Let me start with a strange question. What if the reason we haven't met aliens has nothing to do with intelligence, technology, or distance? What if the real problem is time itself? Because when most people imagine interstellar travel, they picture a spaceship crossing the galaxy the way airplanes cross continents. You take off, travel for a while, and eventually arrive somewhere else. But here's what's really going on in the universe. The moment you start traveling close to the speed of light, time itself begins to behave differently. And this is not science fiction. This is Einstein's theory of relativity, one of the most tested frameworks in physics. According to relativity, as an object moves faster and faster through space, time slows down for that object relative to everything else. Physicists call this time dilation. Let me explain this with a simple analogy. Imagine two clocks. One stays on Earth. The other goes on a spaceship traveling extremely close to the speed of light. To the astronaut, everything feels normal. Their heartbeat, their breathing, their thoughts, all moving at the same pace. But when they return home, the clock on Earth has moved much further into the future. In fact, according to relativistic calculations, a journey that feels like a few years for the traveler could mean centuries have passed back home. Now pause for a moment and think about what this means for an advanced civilization exploring the stars. Every explorer they send into deep space is essentially jumping into the future relative to their home planet. Communication becomes almost impossible. Civilizations become disconnected from their explorers, and over interstellar distances, the time gap becomes so large that explorers could return to a civilization that no longer exists. So here's the fascinating possibility. Maybe advanced civilizations don't spread across the galaxy easily, not because they lack technology, but because the universe itself makes it incredibly difficult to stay synchronized in time. In other words, the cosmos might not just be vast in space. It may also be fractured in time. And that brings us to the real question we're going to explore today. What if alien civilizations exist, but the physics of the universe traps them in different timelines of experience, making contact incredibly rare? In this talk, we're going to break down the real physics behind this idea, step by step, using the same clear, practical reasoning great teachers like Richard Feynman loved. And by the end, you'll understand something profound. The greatest barrier between civilizations might not be distance. It might be time itself. If you enjoy exploring the deep physics of the universe explained simply, consider subscribing. I share content like this regularly. Now let's break this problem down scientifically. Because once you understand the mechanisms, the idea that aliens are stuck in time starts to make a surprising amount of sense. Before we go deeper, let's map out the 6 scientific ideas that explain why interstellar civilizations may effectively become stuck in time. Because once you understand these mechanisms, something surprising emerges. The universe doesn't just limit travel through distance, it also limits civilizations through time, energy, and communication. Think of this like a whiteboard roadmap. Each concept builds on the previous one. Here are the 6 insights we're going to explore. First, the speed of light is a hard cosmic speed limit. According to modern physics, nothing with mass can travel faster than light. This isn't just a technological limitation, it's built directly into the structure of space-time itself. Even extremely advanced civilizations would still have to obey this rule. And when distances between stars are measured in light years, that limitation becomes enormous. Second, time dilation changes the timeline of travelers. When objects move close to the speed of light, time slows down for them relative to stationary observers. A crew traveling across the galaxy might experience only a few decades, while thousands or even millions of years pass for the civilization they left behind. Third, communication across interstellar distances is painfully slow. Even light-speed signals take years, centuries, or longer to reach their destination. This means a message sent to a distant colony might not receive a reply until generations later. Coordination between civilizations becomes extremely difficult. Fourth, the energy required for relativistic travel is astronomical. Accelerating a spacecraft with significant mass anywhere near the speed of light requires energy comparable to the output of entire planets or stars. Even advanced technology cannot bypass the basic equations of physics. Fifth, cosmic distances are far larger than most people imagine. The nearest star system is over 4 light-years away. Our galaxy contains roughly 400 billion stars, spread across a disk about 100,000 light-years wide. Crossing meaningful portions of that distance becomes a timescale problem, not just a transportation problem. And sixth, perhaps the most fascinating idea of all, Civilizations may evolve and disappear faster than interstellar contact can occur. If technological civilizations only last a few thousand or tens of thousands of years, the odds of two civilizations existing at the same time and within reachable distance become extremely small. So when you combine these six realities, speed limits, time dilation, communication delays, energy costs, vast distances, and limited civilization lifespans, something remarkable appears. The universe may not prevent intelligent life from existing, but it might naturally separate civilizations across different eras of cosmic time, almost like ships passing each other in the dark ocean of the galaxy, except they're separated not just by space, but by centuries, millennia, or even millions of years. Now let's take the first concept and examine it carefully, because everything begins with a simple but powerful rule of physics. The speed of light is the ultimate speed limit of the universe. Now let's take the first idea and slow it down, the way a good teacher would at the whiteboard. Because everything in this conversation starts with a very simple rule of physics. Nothing with mass can travel faster than light. The speed of light is about 299,792 kilometers per second. That's roughly 186,000 miles every second. In a single second, light could circle the Earth more than 7 times. It's unbelievably fast by everyday standards. But here's the surprising part. Even at that incredible speed, the universe is so large that travel still becomes painfully slow. Let me explain this with a simple analogy. Imagine you shrink the solar system down so that the Earth is 1 meter from the Sun. On that scale, the nearest star system, Alpha Centauri, would still be about 270 kilometers away. That's like driving from one city to another. Now remember, that's the closest star system. Most stars in our galaxy are thousands of light years away. Our galaxy itself, the Milky Way, stretches roughly 100,000 light years across. So even if a civilization could travel at 10% of the speed of light, which would already require unimaginable technology, reaching a star 100 light years away would still take 1,000 years. And here's what's really going on inside the physics. As an object accelerates toward the speed of light, its energy requirement increases dramatically. This comes directly from Albert Einstein's famous equation, E = mc². But in relativistic motion, the effective mass of an object increases as velocity approaches the speed of light. That means every additional increase in speed requires exponentially more energy. Eventually, reaching light speed would require infinite energy, which means it simply cannot happen. What the research shows is that even extremely advanced propulsion concepts, nuclear fusion drives, antimatter engines, or light sails, would still take decades, centuries, or millennia to cross significant portions of the galaxy. So the universe has quietly installed a rule, not a technological rule, a cosmic rule. The faster you try to travel, the harder the universe pushes back. Now here's where this becomes fascinating for the alien question. If civilizations are bound by this speed limit, then interstellar exploration automatically becomes a multi-generational project. Imagine launching a mission that will not arrive for 500 years. The people who launched it will never see the result. Their children won't either. Their great-great-great-children might be the first to hear the reply. And that creates a new kind of challenge, not engineering, but civilization stability. Because for a project like that to succeed, the society that started the mission must survive long enough to care about the outcome. And that brings us to the second key idea. Because once you try to solve the distance problem by traveling faster, something strange begins to happen. Time itself begins to change. And when that happens, explorers may not just be traveling through space. They may be jumping into the future. If this breakdown is helping you see the universe differently, consider subscribing. I share explorations like this regularly, turning complex physics into ideas you can actually visualize. Next, we'll unpack one of the strangest and most beautiful discoveries in physics, time dilation, and why interstellar travelers may become disconnected from their own civilization. Now let's move to the second idea, and this is where things start to feel almost like science fiction. But it isn't. It's a direct consequence of the physics described by Albert Einstein in the early 20th century. The concept is called time dilation. Here's what's really going on. According to Einstein's theory of special relativity, time is not absolute. It doesn't tick at the same rate for everyone in the universe. Instead, time depends on how fast you are moving. Let me explain this with a simple analogy. Imagine two identical clocks. One stays on Earth. The other boards a spacecraft traveling extremely close to the speed of light. To the astronaut on the spacecraft, everything feels perfectly normal. Their heartbeat, their thoughts, their conversations, Time feels the same, but from the perspective of observers on Earth, something strange is happening. The astronaut's clock is ticking more slowly. This isn't theory anymore. We've measured it directly. Experiments using ultra-precise atomic clocks on high-speed aircraft and satellites consistently confirm time dilation. In fact, systems like the Global Positioning System must account for relativity, or their positioning calculations would drift kilometers each day. Now let's apply this to interstellar exploration. Suppose an alien civilization sends a spacecraft traveling at 99% of the speed of light. For the travelers, the journey might feel like 10 years. But when they return home, more than 70 years could have passed on their planet. Push the speed even closer to light, and the effect becomes even stronger. A traveler could experience only a few decades, while centuries or millennia unfold back home. So here's the strange consequence. Explorers who leave their civilization may return to a future they no longer recognize. Their language may have changed. Their society may have evolved. Their entire culture could be different. Or worse, it might not exist at all. In other words, interstellar explorers don't just travel through space, they jump forward through time, and if a civilization sends out many such missions, something interesting begins to happen. Their explorers slowly drift into different eras of history. Each mission becomes slightly disconnected from the civilization that launched it. Now imagine a galaxy full of civilizations attempting this. Some explorers may arrive at star systems long after another civilization has already vanished. Others may leave messages that won't be received for thousands of years. This means intelligent life might be everywhere, yet still incredibly difficult to encounter. Not because no one is traveling, but because everyone is experiencing different timelines. If this idea is making the universe feel a little more mysterious, that's a good sign. It means you're starting to see the deeper structure of reality. But the time problem gets even bigger when we consider communication. Because even if civilizations survive long enough to explore, they still have to talk to each other across interstellar distances. And that introduces the third barrier, one that may isolate civilizations across the galaxy: the speed of information itself. Now let's examine the third barrier, and this one is often overlooked. Even if a civilization solves propulsion, even if they can travel near the speed of light, they still face a very stubborn problem: communication, because in our universe, information cannot travel faster than light. This rule comes directly from the structure of space-time described by relativity. So imagine two civilizations trying to communicate across interstellar distances. Let's start with something relatively close. The nearest star system to us is Alpha Centauri, about 4.37 light-years away. That means if Earth sent a message today, a radio signal, a laser transmission, any form of electromagnetic communication, it would take 4.37 years just to arrive, and another 4.37 years for a reply. So even in the best-case scenario, a simple question and answer would take almost 9 years. Now extend that across the galaxy. The diameter of the Milky Way is roughly 100,000 light-years. If two civilizations were separated by only 10,000 light-years, a message would take 10,000 years to arrive, and another 10,000 years for the reply. That means a single conversation could take 20,000 years. Let me explain this with a simple analogy. Imagine trying to run a modern company where every email takes 20,000 years to receive a reply. You send a message about a decision. By the time the answer arrives, your entire organization, language, and culture have changed. The original question might not even make sense anymore. This is the fundamental communication challenge of the cosmos. Civilizations cannot coordinate across large distances because information simply moves too slowly. And what the research shows is that our own attempts to search for extraterrestrial signals face this exact problem. Projects like SETI Institute scan the sky for artificial radio signals that might come from distant civilizations. But even if a signal is detected, it might have been transmitted thousands or millions of years ago. The civilization that sent it could already be extinct. In other words, when we look into space, we're not just looking across distance, we're looking back through time. The stars we see tonight are ancient messages traveling across the universe, and the same rule applies to alien civilizations. Their signals, if they exist, are fossils of communication moving slowly across cosmic distances. Now think about what this means for interstellar societies. If they build colonies across multiple star systems, those colonies become separated by decades, centuries, or millennia of communication delay. Eventually, each colony evolves independently. Languages change. Cultures diverge. Biology might even adapt to different planets. After enough time, those colonies might no longer feel like one civilization at all. They become separate civilizations. So even if intelligent life spreads across the galaxy, it may fragment into isolated islands of culture, each living on its own timeline. And that brings us to the fourth constraint. Because distance and communication are only part of the challenge, the deeper barrier may be something even more fundamental: energy. The energy required to move civilizations across interstellar space may be so enormous that only a tiny fraction of species could ever attempt it. And that changes the entire equation of cosmic exploration. Now let's talk about the fourth constraint, and this one may be the most practical limitation of all: energy. Because even if the laws of physics allow something, that doesn't mean it's easy to do. You still have to pay the energy cost. Let's go back to the whiteboard for a moment. Imagine a spacecraft with the mass of a large commercial airplane. To accelerate that mass to even 10% of the speed of light requires an amount of energy comparable to the total energy consumption of an entire civilization for years. And as velocity increases, the energy requirement grows dramatically. This comes from the relativistic equations derived from the work of Albert Einstein. As an object approaches light speed, its kinetic energy increases toward infinity. In simple terms, the closer you get to light speed, the more the universe demands absurd amounts of energy. Let me explain this with a simple analogy. Think of pushing a car on flat ground. At first it's easy. You apply a little force and the car begins moving. But now imagine that the car becomes heavier every time it speeds up. The faster it goes, the heavier it becomes. Eventually, pushing it even a tiny bit faster requires 10 times more effort, then 100 times more, then 1,000 times more. That's essentially what happens to spacecraft at relativistic speeds. Now consider the energy sources civilizations might use. Scientists have proposed several possibilities: fusion propulsion, where hydrogen atoms combine to release enormous energy; antimatter engines, which could theoretically convert nearly 100% of mass into energy; and massive laser-powered light sails, an idea explored by projects like Breakthrough Starshot. But even these concepts come with staggering engineering challenges. To accelerate a small probe using a laser sail, you might need laser arrays generating power comparable to large power plants, and that would only accelerate tiny spacecraft weighing a few grams. Transporting large crews, ecosystems, or entire civilizations would require energy on a scale closer to planetary infrastructure. So here's what's really going on. Interstellar travel is not just a technological challenge, it's an economic and energetic challenge. Civilizations must decide whether spending enormous amounts of energy on interstellar missions is worth it. And many might conclude that it's simply more practical to invest that energy into improving life within their own star system. After all, a single solar system can contain enormous resources: planets, moons, asteroids, and energy from its star lasting billions of years. So instead of spreading across the galaxy, advanced civilizations may choose to optimize locally. They may become incredibly advanced within their own systems, but rarely attempt the enormous leap between stars. If this explanation is helping you think about the universe in a new way, consider subscribing. I share ideas like this regularly, breaking down complex science into clear mental models you can visualize. But even if a civilization overcomes the energy barrier, there's still another problem waiting. Because the scale of the galaxy itself introduces a challenge so large that most people simply cannot intuitively grasp it. To understand why aliens may be stuck in time, we have to confront the fifth reality. The galaxy is far larger than our brains are designed to imagine. Now let's confront the fifth reality, and this is where our human intuition begins to fail us. Because the scale of the universe is so enormous that our brains simply aren't designed to visualize it correctly. We evolved to understand distances like meters, kilometers, maybe even the distance between cities. But when we talk about the galaxy, we're dealing with distances measured in light years, and that changes everything. A light year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In 1 year, light travels nearly 9.5 trillion kilometers. Now let's put that into context. The nearest star system to Earth is Alpha Centauri, about 4.37 light-years away. That means even light, the fastest thing in the universe, takes more than 4 years to get there. Now consider our galaxy, the Milky Way. Astronomers estimate it contains somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years wide. Let me explain this with a simple analogy. Imagine shrinking the Milky Way down so that the distance between stars is the distance between grains of sand scattered across a beach. Even then, the beach would stretch thousands of kilometers. That's the kind of scale we're dealing with. Now here's why this matters for alien civilizations. Even if a civilization builds spacecraft capable of traveling at 10% of the speed of light, crossing the Milky Way would still take 1 million years. 1 million years. To understand how long that is, consider this. 1 million years ago, early human ancestors were still using primitive stone tools. Our entire recorded human history, agriculture, cities, science, technology, fits into roughly the last 10,000 years. So a journey across the galaxy would last 100 times longer than human civilization has existed. This introduces a profound problem. Civilizations themselves may not last long enough to complete interstellar expansion. Astrophysicists studying the Fermi paradox often point to this issue. If intelligent civilizations typically last only a few thousand or tens of thousands of years before transforming, collapsing, or evolving into something else, then galaxy-spanning exploration becomes extremely difficult. Explorers may launch missions that will take hundreds of thousands of years to reach distant regions. By the time those missions arrive, the civilization that launched them may have changed completely or vanished. So instead of galaxies filled with interacting civilizations, what we might actually have is something very different. A galaxy where civilizations appear, evolve, and disappear, scattered across vast stretches of space and time, almost like sparks appearing briefly in a dark cosmic forest. Sometimes two sparks may appear near each other, but most of the time they never overlap. And that leads us to the sixth and perhaps most fascinating insight of all. Because the real reason aliens may seem absent might not be distance, energy, or technology. It might simply be that civilizations don't exist long enough at the same time to meet each other. In other words, intelligent life might be common in the universe, but civilizations may rarely share the same moment in cosmic history. Now let's explore the sixth and perhaps most profound insight. Because even if the universe contains many intelligent civilizations, there's a hidden variable that may prevent them from ever meeting: time. More specifically, how long civilizations actually last. This question sits at the heart of one of the most famous puzzles in astrophysics, the Fermi paradox. In simple terms, the paradox asks, if the universe is so vast with hundreds of billions of stars in the Milky Way alone, then why don't we see evidence of advanced civilizations everywhere? Where is everybody? One possible answer is surprisingly simple. Civilizations may not last very long. Let me explain this with a practical analogy. Imagine the entire history of the galaxy compressed into a 24-hour day. The Milky Way formed roughly 13 billion years ago. Human technological civilization, radio signals, satellites, modern science has existed for about 100 years. On that 24-hour clock, our technological civilization would appear only in the final fraction of a second before midnight. That's how brief our presence is so far. Now imagine thousands or even millions of civilizations appearing throughout cosmic history. Most of them might exist for a few thousand years, perhaps longer if they survive technological risks. But the galaxy evolves over billions of years, so the probability that two civilizations exist close enough in both space and time to detect each other may be extremely small. In other words, civilizations may be separated not just by distance but by millions of years. One species might explore the stars long before another evolves intelligence. Another civilization might arise long after the first one disappears. It's like walking into a forest where campfires occasionally appear in the night. Each fire burns for a while, then it fades. Another appears somewhere else, at another time. But rarely do two fires burn close enough together to see each other. So the universe might not be silent because life is rare. It might be silent because civilizations are out of sync in time. Some may have existed millions of years before us. Others may emerge millions of years in the future. And explorers traveling between stars may unknowingly arrive too early or too late. This idea changes the alien question completely. Instead of asking, where are the aliens? A better question may be, when were they? Or even more intriguingly, when will they be? If this way of thinking about the universe fascinates you, consider subscribing. I post explorations like this regularly, breaking down deep scientific ideas so they become clear and visual. Now let's bring everything together. Because when we combine the physics of speed limits, time dilation, communication delays, energy constraints, cosmic distances, and civilization lifetimes, a new picture of the galaxy begins to emerge. So let's step back and put the whole picture together. Because once we connect all these pieces, the silence of the universe starts to make a lot more sense. First, the universe imposes a strict speed limit. Nothing with mass can travel faster than light, a consequence of the physics described by Albert Einstein. That means interstellar travel is automatically slow when measured against the enormous distances between stars. Second, when civilizations try to solve the distance problem by traveling extremely fast, they encounter time dilation. Travelers experience time more slowly than the civilization they left behind. In practical terms, explorers can return to a future that is centuries or even millennia ahead of their departure. Third, communication itself becomes a barrier. Even light-speed signals take years, centuries, or thousands of years to cross large regions of the galaxy. That makes coordination between star systems incredibly difficult. Fourth, the energy cost of relativistic travel is staggering. Accelerating even a small spacecraft to a fraction of light speed requires enormous power, potentially the output of entire planetary infrastructures. Fifth, the scale of the Milky Way is almost impossible for the human brain to intuitively grasp. With hundreds of billions of stars spread across 100,000 light-years, crossing meaningful portions of the galaxy could take hundreds of thousands or even millions of years. And sixth, civilizations themselves may not last long enough to overlap in time. This is one possible explanation behind the famous Fermi paradox. When you combine all six of these realities, a new perspective appears. The universe may not be empty, it may simply be out of sync. Civilizations might rise and fall at different times. Explorers might travel between stars only to arrive long after another civilization has disappeared. Signals may drift across space for thousands or millions of years before reaching anyone capable of hearing them. In other words, intelligent life might exist throughout the galaxy, but separated not just by distance, separated by time, almost like travelers moving through different chapters of the same cosmic story, and that leads to a fascinating possibility. The reason we haven't encountered alien civilizations may not be because they never existed. It might be because their moment in history was different from ours. Some may have lived millions of years before humanity appeared. Others may emerge millions of years in the future. So here's the challenge I'll leave you with. The next time you look up at the night sky, remember that you're not just looking across space, you're looking across time. Some of the stars you see are sending light that began its journey before human civilization even existed. And somewhere out there, perhaps right now, another civilization may be asking the same question we are. Are we alone? If this exploration helped you see the universe in a new way, take a moment to like the video and subscribe. Join a growing community of people curious about science, the cosmos, and the deeper laws shaping our reality. Because sometimes, the biggest discoveries don't just change what we know, they change how we think about our place in the universe.